Hi, guys and gals. It's Mr. Tima here. We're going to be talking about magnetic fields. Okay, so section 6.4 magnetic fields. I love this picture. Really cool picture of the sun and how it's always putting these photons at us. And this is literally what the Earth's magnetic field is doing, basically, a force field kind of protecting us from all that kind of stuff. So, all right, here we go. So here are our assessment statements. All right. So a magnet. Okay. So what is a magnet? Okay. You guys know what magnets are. You've probably talked about magnets. Magnets has magnetic poles called dipoles. Okay. And what's crazy about these dipoles is here. I need to move myself out of the way for this slide, don't I? There we go. But what's kind of crazy about these dipoles is that what we have here is you always have a north and south pole. The north is usually considered the positive, and the south pole is usually considered to be negative. Okay, what's interesting about magnets is if you cut magnets in half, it's not like you have a pure negative and a pure positive. Okay, when you have dipoles, when you cut a magnet in half, you get a north pole, south pole, north pole, south pole. Unlike a diode or a monopole, when you cut it in pure half, you get a true positive and a true negative. That's electricity. Electricity, you can have pure positive and pure negative, like when we did the electroscopes and things like that. But when we have a dipole, like a magnet, when you cut a magnet in half, you still have a north-south, a north-south. Okay, kind of crazy to think about. All right. I don't know why I'm not hiding this. Okay. So again, north south, obviously, you know that like charges repel and opposite charges attract. Okay. So you guys all know that. You should be ready to go with that. All right. So you should have watched the Faraday video. You should have watched the Faraday video. I can pull myself, keep moving myself around the screen here. All right. But you should have watched the Faraday video. If you have not watched the Faraday video, then you need to go on there right now, back to the folder and open up the Faraday video and watch that so that you can see the great visual representation. But in essence, if we have a magnetic field flying out of here and flying out of here like this, and it keeps wrapping around more and more, basically, these can ride on the current. Okay, these guys can ride on those currents like sails on wind. All right. So again, you have to imagine in a wire that this magnetic field is constantly just flowing around here. All right. So again, remember, we would assume that this is a positive pole and this is a negative. Remember, because positive, you emanate outwards, and negative, everything comes in with you. All right. So we did that experiment earlier in the year, the simulation with the charges. It's the same with the magnetic field. You can kind of see how these little sails are flying around with the field. And this is basically how the Earth looks as well. Example of the Earth's magnetic field, which is interesting because the Earth's magnetic field, the north side is actually negative and the south is actually positive. Okay. And those poles will actually flip over time. It's not like the world will come to an end, they'll just flip instantaneously. So there you go. So when you look at a compass, when you have a compass and we say the compass points north, when our compass points north, well, that compass, that north little needle is actually charged positively. That's why you're able to like in electrostatics, you can actually rub a needle and put it on water on a leaf and it will point north because that positive is attracted to the north pole. Alrighty. So there's a term that we need to know, and that is flux. Okay. Anybody know where this is from? Anybody know where this picture is from? It's from a movie called Back to the Future. Okay, and it's the flux capacitor. Well, flux is measured in something called a Tesla, capital T. All right, but magnetic flux is basically the field strength. Okay, its symbol is B, but its unit is T. Okay, so its symbol is B, but its unit is Tesla. All right. Okay. So here we go. This is called the right-hand rule. And there's two different ways we have to talk about this. The right-hand rule when we are discussing about a wire or when we're talking about into the page and out of the page. It's going to be hard. That's why I have the video on so you can look at this. But if you think of a wire, okay, when you think of a wire, it's very simple. You need to use your right hand. Okay, literally, it's called the right hand rule for that reason. You have to use your right hand. Okay, your thumb follows the current. So you can think of your thumb as moving in the positive direction. So if I had a wire or this marker and my thumb is going up like the picture right here, all right, it's going up like the picture here. All right, thumb goes up, that's the current. Which way would the magnetic field go? Well, the magnetic field is going for me, if you look at this, and you kind of have to do this with a pencil in front of you because it's probably opposite in the picture. But if my thumb is up, then my hand is moving counterclockwise. And that's what's happening here. If we flip the current and the current was going down, now my fingers, which are the field, would be going clockwise. Okay, so just by knowing the direction of the current, we know which direction the magnetic field is turning. Literally, if we run a current through this wire right here, and we leave it, this is magnetic sand. And what they did is they ran this current through here and they let the sand sit here, and the sand naturally started vibrating into these magnetic field patterns. And if the current was going that way, if I is going this way, then we know that B, the magnetic field, is moving in this direction, okay, in a counterclockwise direction. All right. Now, when we start running coils, when we take this marker and we start bending this marker into a coil, things start to happen. The magnetic field it continues to do the same thing, but now you have to think about it. So let's pretend the marker is facing me. That would be this section right here. My magnetic field would be wrapping still counterclockwise. So it's kind of coming around this direction. We're only right here. We're only right here in this section. Okay, as the marker starts to bend up, so take your marker, it's facing you, and now it starts to bend up, right? Still, my thumb is up. I know it's hard to see. My thumb is up, but my hand is still going counterclockwise. It's kind of wrapping through it. As my hand continues to go, you're going to notice that this thing still continues to wrap through. It's still moving counterclockwise. Okay, counterclockwise. But now on this end, as that marker comes around the loop, now this end, the marker is facing down. Okay, so the current would be down, and my hand now on this side, you know, to the downward, in my point of view, is now moving clockwise. But still, if you think about it, it's wrapping around here and coming through. So basically, all of these are wrapping through, and we get this general kind of direction kind of going through the tube, shooting through here. And that's kind of what this is showing, how this guy's spinning through here. This guy's spinning through here. Okay, and we get this general giant force pushing through this way. Now that's important. That seems really simple, but it is really important because there are these things called solenoids, and these solenoids are everywhere, and we don't even notice them all the time of what they're in. But they come all the way down to how a pop machine works. When you put the money in the pop machine, you push the button, it sends an electrical signal. That electrical signal runs a current through this wire, which allows this to pop. There might be a metal bar in here, and this metal bar kind of shoots. Well, that's what drops the pop can. Okay. It could be in your car. Your car does this to freeze your seatbelt. When the sensors pick up something, it will shoot a current through a wire in one direction, which sends a bolt shooting there and it seals your seatbelt. It could be the door locks up and down. You ever wonder why when you push the button, lock and unlock, it knows which way to go? Because when we push lock, let's say it's lock, it shoots the current this way, which sends the pin and locks it. When you push the opposite button, the current goes the other way, which flips this magnetic field, flips the solenoid, and it'll go this way. Again, so this is a very interesting thing that kind of leads us to a lot of mechanical motion. Here's just a nicer picture of it. If you want to, your thumb would be the eye. You can think about if this is the thumb, if this is a tube, eyes going up, which way would that direction go? All right. Now, how do we calculate this stuff? Well, first of all, there is a way to determine that force of how much the bolt will move. Well, here's how we do that. The saying is, what the F, Bill? Do you see this? It's B-I-L. What the F, Bill? Okay, where B is the magnetic field, I is the current, and L is the length of the wire. The more wire we have, the more coil we can have, the more force we can have. All right, here we go. So right here, I'm going to change up my color. I like that magenta that we used earlier. It was kind of a neat color. This is what we were talking about. This is what we've been doing with a wire like this, wrapping around, thumb up, wrapping around. Now, we're going to talk about what's called the true right-hand rule. Again, your thumb is still the current, just like your thumb is the current here. All right? Your fingers are the magnetic field, the B, just like it is here. But now we're going to assume that our palm, perpendicular to our palm, like our palm is shooting out, is the force. Now, some people like to point their finger, like thumb for current. These three fingers are the magnetic field, and some people like to do, it's hard to show here, but they like to do this finger as the force, because now we see that it's pointing kind of off of our palm. Okay, and we'll work on this in class. Okay. All right, let's do a quick little thing here. It says, what is the force? So we're looking for F of a 30 centimeter long straight wire. Are we allowed to leave this in 30 centimeters? I hope by now we're going, nope, that's 0.3 meters of a 2 amp current, I, okay, and has a field flux. That would be what symbol? Yep, that's B, okay, of 6, what's this? Micro Teslas. So remember, 6 micro is 6 times 10 to the negative 6. Okay, so again, hopefully you can take a second, pause it, see where you're at. Great. Hopefully you figured out that you need to do what the F bill, and it's literally just a plug and chug situation again. All right, so it's basically everything we just talked about. There's our 6 micro Teslas. There you go. Boom, boom. And you should have got the answer of 3.6. All right. So this drawing's good, but I kind of hate it at the same time. So remember, magnetic field, we're talking about our 3 fingers here, our 3 fingers or our fingers. Which way are they pointing? Well, what we do is we say if the magnetic field is facing into the page, we actually put the symbol X on our paper. When it's coming out of the page, we put a dot. And the way this is drawn, I hate how they have the arrows drawn, but what they're trying to show you is what part of the arrow. What they're saying is if it went into the page, then it's already gone through the page, and what you would see is an X pattern, because like the arrows on the back of, or excuse me, the feathers on the back of the arrow would have gone through the page already. So you would see what's left over. On a coming out of it, it's like you just see the tip of that arrow coming out at you. So it would just be a dot, and that would be coming out of the page. How I like to remember it too is like when we go digging for buried treasure, we dig into the ground. Remember, X marks the spot of where we dig at. Okay. All right. And then what I always think of too, being from, the country, is if you see a hole in the ground, usually something likes to come out of the hole at you. Okay. Like it could be a little snake or a little animal or something. So X marks the spot. We're going into the page. We're digging into the page, little hole. Something could jump out at you out of a hole. Okay. All right. Let's see. Can you put your hand in this? How would your hand look? See if you can do it right now. First of all, remember, what's I? I is the current. Okay, I is the current. So my thumb is going to be up. X's mean what? X's mean X marks the spot. We are digging into the page. So that means my fingers, not my thumb. My thumb is up, but my fingers are literally going into the page. They're coming, it's like you're pointing right at your screen. All right. And the magnetic field force, which is either you need to think of it as your palm, or you can put this finger perpendicular so it kind of like looks like that, okay? All right, but so thumb up, magnetic field into the page, and then we want to have our finger or our palm facing left, okay? So hopefully you did that right, okay? While I'm thinking about it, remember, this is current. This is a positive charge. If it tells you the electrons, which are negative, electrons would be pointing down. So we actually know that opposite the thumb, there's electrons, okay? All right, let's see if we can put our hand in this direction. Let's try to do this one right here. This is the current. Remember, current is I. Electrons would be opposite. Magnetic field's in X. What does that mean? What does that mean? That means we're going, X marks the spot. We're going into the page. We're going into, in this case, because these are X's. If they were dots, we'd say they're out of the page, and the force is down. All right, take a second, see if you can figure out how your hand would go. All right, my thumb should be going left. I know it probably looks right on the screen, but it's like if I'm facing the screen, my thumb should be going left. My fingers should be going literally into the screen that you're looking at. And look at where my finger is. My finger is pointed down, and that's good because that blue arrow is down and the force should be down, or my palm is down. Either way. All right. If you look at the bottom picture, nothing's really changed except for the force. Okay. So if you go like this, you can kind of move your hand to follow that circle, and you kind of break your hand a little bit as you flip around. Okay. Because you're trying to follow that as it goes around the screen. All right. So basically, just having some pictures here to show you that when the forces are like, if we had two wires, think about this. If I had two wires running in the same direction with the same current running through them, notice they are the same field. They're going to do here. What do you think? Things that are like the same fields, if you're on the same team, shall you say, this field's going to grow together. It's actually going to add together. Okay, it's going to keep adding together. It's just going to get bigger and bigger. It's all one field. It's a horrible drawing, but you get the point. If they're in opposite directions, then it's kind of like they're opposing each other. So instead of growing together, as these two approach each other, we're not going to join together. So they're going to kind of like repel each other. So unlike charges, right? Like charges repel and opposite charges attract. Fields aren't like that. You have to be on the same team so your force fields work together. If you're on opposite teams, they don't want to join together. All right, and this is the last time you'll see this. Picture. But remember when we talked about gravitation? If you remember, that was a big G, right? Big G, M1, M2 over R squared. Okay, remember with electricity, that was K, a constant. We're dealing with charges now, but it's basically, Q1, I almost wrote M again, Q1, Q2 over R squared. But now with magnetic field, we actually have a different formula, and that formula is what the F bill. Okay, what the F bill. We don't really care. They kind of follow a little bit different rules here. Okay, so again, there's your formulas, but here's how they're all related. So these two are very similar to each other. These two, very similar to each other. This guy's kind of the oddball. It's that third force, and they talk about that in the Faraday video as well, which again, if you haven't watched yet, you need to watch before you were supposed to come back to these notes. All right, we are going to do some of these problems. I will help modify them, and I'll have them up for you. Again, hope you enjoyed these. It's a little hard to show you this stuff, so make sure you tune into class so that we can talk about this. Until next time, Mr. Tima, out.